Welcome back to the deep dive. Today we're jumping into something fascinating, the world of super strong materials. Think aerospace, high performance cars.
Absolutely. We're focusing on carbon fiber reinforced polymers, or CFRPs,
Yes.
stuff that needs to be incredibly light, but also incredibly tough.
Yeah.
Formula One, wind turbines, aircraft structures.
Right, they're everywhere in critical applications. But here's the tricky part, the paradox really. These things are built in layers, right?
Exactly. Layer upon layer of carbon fiber infused with a polymer resin.
And that layering process, it's not always perfect. You can get these hidden flaws baked right in. Things like voids or wrinkles in the fibers.
That's the core issue. These aren't just surface scratches, they're internal defects.
Yeah.
And they can be really tough to spot using standard inspection methods.
So we're digging into some specific research today.
Yeah, a really insightful study by Slovikov and colleagues. They look specifically at how these defects behave under shear loading.
Shear loading. Remind us what that is again.
Think of sliding forces, like where a plane's wing attaches to the fuselage, or bolts connecting composite parts. Those joints experience a lot of shear. It's a really critical stress state for these materials.
Okay, so this study didn't just look at perfect materials. It looked at flawed ones under that specific kind of stress.
Precisely. Their goal was to quantify how much two really common defects, voids and wrinkles, actually weaken the CFRP when you put it under shear.
And they used a pretty standard type of CFRP.
Yes, a structural grade one, the kind you'd actually find in use. It had a 090 layup, which is very common fibers running at 0 and 90 degrees, stacked up, 10 layers thick.
So our mission here is basically to pull out the key numbers, the key findings from their work.
Exactly. What can this tell engineers, manufacturers? What does it mean for deciding if a part is safe or for improving non-destructive testing in DT?
All right, let's get into the flaws themselves. First up, voids. What exactly is a void in this context?
Okay, so imagine when they're making the composite, they're infusing the fibers with liquid resin. If that resin doesn't quite reach everywhere, you get a dry spot.
Ah, okay.
Or you could just trap tiny air bubbles during the layup process or when it's curing under heat and pressure. These become voids, basically, little empty pockets inside the finished material.
Sort of like an air bubble trapped in concrete, but on a much finer scale.
A good analogy, yeah.
Yeah.
They're definitely a sign that the manufacturing wasn't absolutely perfect.
And the researchers didn't just wait for random voids to appear, did they? They controlled this.
They did, and that's crucial for getting reliable data. They actually inserted artificial voids. They used a very thin film, like Teflon, cut into specific shapes.
Which shapes?
They tested two, a 20 millimeter diameter circle and a 20 by 20 millimeter square.
Yeah.
And they placed these very deliberately right in the middle of the layer stack, between the fifth and sixth layers.
Okay, so controlled size, controlled location. And how much of the material cross-section did these voids take up?
They calculated the area fraction, which they called kV dollars. For these voids, it was 5.3%. So about 5% of that central area was just empty space.
Got it. Now what about the other defect-type wrinkles? That sounds different.
It is. Wrinkles aren't empty space. They're more about the fibers themselves being wavy or bunched up instead of long, perfectly straight and flat within their layer.
Like a ripple in a carpet.
Exactly like that. It's a distortion of the reinforcement. And these are also process-induced.
Yeah.
Maybe from how the layers are laid down or handled before curing.
And did these wrinkles take up more or less area than the voids?
In this study, the wrinkles they created had a higher area fraction, kilodollars, about 10.5%. But here's a really key difference.
Oh.
Because the fibers were bunched up, the wrinkled sections were actually thicker than the rest of the material. The specimens with wrinkles ended up being about 10% thicker, 2.2 millimeters versus 2.0 millimeters for the perfect ones.
Huh. So a wrinkle isn't just a flaw, it actually changes the local geometry by adding bulk, like having 12 layers locally instead of 10.
Essentially, yes. That becomes important later. So we have these two defect types, the whole void and the bump wrinkle.
Right. So how did they test them? How do you apply pure shear?
They used a standard test method, ASTM D7078. It involves a specific sample shape and loading fixture designed to make the central gauge section experience shear stress when you pull on it with a testing machine. They used an Instron system.
Okay, standard mechanical testing. But they added something else, didn't they?
Yes, digital image correlation, or DIC. This is super useful for composites.
Explain DIC quickly. It tracks movement.
Basically, yeah. You put a random speckle pattern on the sample surface, and cameras track how those speckles move in 3D as the material is loaded. It creates these incredibly detailed maps of strain and deformation across the surface.
So you can see exactly where the stress is concentrating and how the failure starts, not just when it breaks.
Precisely. You can see if the failure starts right at the defect, how it spreads. It gives you way more insight than just the final breaking load, especially important when you have these internal flaws.
Okay, makes sense. So let's get to the results. What was the starting point? The performance of the perfect no-defect samples.
Right, the baseline. These average an ultimate shear strength of 72.1 megapascals MPa. That's the peak stress they could handle.
And their stiffness.
Their shear modulus, which is the measure of stiffness in shear, was 4.49 gigapascals GPa. So 72.1 MPa strength, 4.49 GPa stiffness. Those are our benchmarks.
Okay. Now, bring in the voids, that 5.3% concentration. What happened? Big drop in strength.
This is where it gets interesting. The drop was, well, minimal, only about 2.2% on average.
Only 2.2%, really?
Yeah, the average strength fell to around 70.5 or 70.6 MPa. So barely a dent, really.
And the stiffness, did the voids make it less rigid?
Nope. The shear modulus stayed almost exactly the same, around 4.48 GPa. Essentially identical to the perfect samples.
Wow. Okay, so a 5% hole in the middle only knocked off 2% of the strength and didn't change stiffness at all. That's quite forgiving, isn't it?
It certainly suggests that, at least under these shear conditions, this level of void content isn't catastrophic. But there's another layer to this.
Go on.
Remember, they tested both circular and square voids.
Yeah, and I was thinking the square one with those sharp corners must have been worse. Stress concentrations, right?
That's the standard thinking in fraction mechanics, absolutely. Sharp corners usually act as stress risers and initiate failure much earlier.
So the square voids failed at a lower stress.
They didn't. Statistically, there was no significant difference in the ultimate shear strength between the samples with circular voids and those with square voids.
Wait, what? The shape didn't matter. A sharp corner versus a smooth circle made no difference to the breaking point.
Apparently not. For this specific test setup and defect concentration, it was one of the most counterintuitive findings.
No. How do they explain that?
The interpretation is that under this type of shear loading, the failure isn't primarily driven by tiny stress concentrations at the void edge. It's more influenced by the overall reduction in load-bearing area caused by the void.
So the amount of material missing, the 5.3% area, was the dominant factor, not the shape of the missing area.
That seems to be the case here. The shear failure mechanism might be less sensitive to those sharp geometric features compared to, say, pulling the material apart in tension.
That is fascinating. It really changes how you might think about NDT results, doesn't it?
It does. Maybe the focus should be less on the exact morphology of a detected void and more on accurately quantifying its overall size or volume fraction, at least for shear critical parts.
So prioritize measuring the how much over the what shape?
Sort of, yeah. And another positive point, despite the defects, all the samples, voided or not, failed in the expected way, vertical shear cracks in the gauge section. The test itself was consistent.
Okay, good. Now let's switch gears to the wrinkles. They had a higher concentration, 10.5%. Did they cause a bigger strength drop?
A slightly bigger drop, yes, but still quite modest. The average shear strength went down by about 3% to around 69.9 MPa.
So double the defect area fraction compared to voids, but only a slightly larger strength reduction, 3% versus 2.2%. Still seems pretty tolerant.
Agreed. But the really weird part was the stiffness.
Ah, right. What happened with the shear modulus for the wrinkled samples?
It went up significantly. Remember, the baseline was 4.49 GPa. The wrinkled samples averaged 5.39 GPa.
How does adding a flaw, a wrinkle, make the material stiffer? That feels completely wrong.
It does seem paradoxical, doesn't it? But remember that physical difference we noted earlier.
The thickness. The wrinkled samples were thicker.
Exactly. The localized waviness of the fibers actually added material bulk in that tested region. Stiffness, or modulus, isn't just about material quality. It's also related to geometry and how much material is resisting the load.
Ah, I see. So the increase in thickness in the wrinkled zone more than compensated for any local weakness or misalignment caused by the wrinkle itself.
That's the explanation offered in the study. The structural effect of the added thickness dominated, leading to a higher overall shear stiffness measurement for that specific gauge section, even though the ultimate strength was slightly lower.
So the wrinkle, while technically a defect, inadvertently reinforced the structure locally in terms of stiffness because it made it thicker.
Kind of a strange trade-off, yeah.
Ooh.
A slight hit on strength, but a boost in stiffness due to that geometric change.
Okay, let's try and summarize that for someone listening, maybe an engineer. For voids at around 5% concentration.
Minimal strength drop, about 2%, and basically no change in stiffness. Shape doesn't seem critical for shear strength at this level.
And for wrinkles at around 10% concentration.
Also a minimal strength drop, maybe 3%, but a noticeable increase in stiffness, likely due to the thickness increase caused by the wrinkle itself.
Right. So both are fairly benign in terms of ultimate shear strength at these levels, but they affect the elastic properties, the stiffness, very differently.
Precisely. And that difference in stiffness could be really important if you're designing something where vibration or dynamic response matters, because modulus drives that behavior.
Okay, this brings us to the big so what question. Why should an engineer or a manufacturer really care about a 2 or 3% drop in strength found in a lab study? Don't they use big safety factors anyway?
They do use safety factors, absolutely.
Yes.
But those factors aren't infinite, especially in weight-critical industries like aerospace. Every bit of performance matters.
So knowing the real impact is important.
Yes. This kind of data allows for more refined defect tolerance criteria. Instead of saying any void is bad, you could potentially say voids below X% concentration are acceptable for this shear-loaded component. It stops you from rejecting expensive parts unnecessarily.
Based on actual performance data, not just assumption.
Exactly. It also helps validate and improve the computer models engineers use. Most simulation models assume perfect materials.
Yeah, the ideal world.
But now you can start incorporating these process-induced flaws into the models and check if the simulation predicts that 2 or 3% strength drop. It makes the digital predictions much closer to physical reality.
And it could guide manufacturing improvements, too?
Potentially, yes. If you know that, say, wrinkles are increasing stiffness in an undesirable way, or that void content above 5% does start to matter more, you can focus process improvements there. And it definitely informs non-destructive testing.
How so? We touched on this, focusing on volume.
Yeah. Instead of just detecting that a flaw exists, the push will be towards NDT methods that can accurately quantify the volume fraction or concentration of porosity, voids. Because this study suggests concentration is a key parameter for shear performance.
So needing NDT, that gives you a percentage, not just a picture.
That's the direction it points, yes. More quantitative NDT.
Okay. So the overall message seems, well, almost reassuring. That these common flaws might not be the immediate deal breakers we sometimes fear, at least under shear.
Cautiously optimistic is probably the right phrase. But, and this is important, we need the scientific caveat.
Ah, the limitations.
Yes. The researchers themselves point out that this study used a relatively small number of samples for each defect type. So, while the results show a very clear trend, they really need confirmation with more tests, maybe different material systems, different layups, different loading conditions.
Science requires replication and broader evidence. Standard procedure.
Absolutely. So we treat this as strong evidence pointing in a certain direction, a very valuable data point, but not the final universal word on all defects under all conditions.
Understood. But the core findings are still significant. Voids impacting strength based on concentration, not shape, and wrinkles affecting stiffness via thickness.
Those are the key takeaways from this specific work, yes.
Okay, let's wrap up then. The researchers usually point towards future work. What's the next big question this study opens up?
Right, so this study looked at voids or wrinkles in isolation. But, in a real manufactured part, you don't usually get just one type of defect neatly by itself.
Ah, you might get both in the same area.
Exactly. Or multiple voids clustered together, or a wrinkle running near the edge. The real challenge, and where research needs to go next, is understanding the combined effects of multiple defects.
How do they interact? Does a wrinkle make a nearby void much worse?
Precisely. How does the spatial arrangement, the scale, the interaction between different types of flaws influence the overall failure? That's much more complex.
And much more realistic.
It is. And understanding that complexity is absolutely crucial if we want to really advance things like digital twins.
Where you build a virtual copy of a real part.
Flaws and all. To accurately predict its behavior and lifespan in service, you need to be able to model not just isolated defects, but the messy reality of how multiple flaws might coexist and interact within the actual component.
Moving from the clean lab setup to simulating the beautiful chaos of the real factory floor and the real stresses, That's the frontier.
It really is. It's vital for making these advanced materials safer and more reliable in the critical applications we depend on.
A fascinating glimpse into that process. Thanks so much for breaking down this research for us.
My pleasure. It's important work.
And thank you all for joining us on The Deep Dive. We'll catch you next time.